The 2021 USU rover team is divided into 5 sub-teams in order to tackle the mission objectives. The 5 teams are Power and Drive, which focuses on suspension systems, wiring, and onboard power management; the Communications team, which focuses on developing the technology necessary to communicate with the rover; the Operations team, which focuses on the onboard robotic arm and control methods; the Programming team, which handles AR tag reading, autonomous traversal, and integrating all systems with the onboard computer; and the Science team, which has researched life detection chemistry and constructed a device to collect and test samples. The chassis for the Sandcrawler rover features dual carbon composite plates that incorporate filament-wound carbon fiber tubes that act as an internal skeleton. 3D printed joints suspend the composite plates and join the internal carbon tubes. The chassis was designed to improve stiffness, strength, and modularity while remaining lightweight. The Power and Drive team has also designed brand new wheel hubs and foam tires that are bonded with polyurethane rubber for traction. These custom wheels increase gearbox to obstacle clearance and allows for more traction via wider tires. We will be using the same mini CIM motors from the Argos rover, but with an adjusted 15:1 gearbox ratio to increase torque. This brings our maximum speed to 2.5 meters per second. The Sandcrawler is also equipped with an emergency stop button that cuts all power to the rover systems in case of emergency. Our team is using a 6 degree of freedom robotic arm, which provides the maneuverability needed to obtain any desired position of the end effector. The arm has demonstrated its capabilities through accomplishing tasks such as opening a drawer and manipulating a 3 kilogram cache, pulling a 5 kilogram object by a rope, typing on a keyboard, inserting a USB drive into a computer, flipping switches and pushing buttons, picking up and retrieving objects, as well as other involved tasks. Users will manipulate the arm with a Mimic controller at the base station. The Mimic controller is a 1-to-1 scale model of the robotic arm used on the rover. A user at the base station will move the Mimic arm to generate positional signals in rotary encoders. These encoders will send the data to the arm on the rover, which will move the robotic arm to match the data. This provides a responsive and intuitive user interface to complete missions both quickly and accurately.
Teleoperation is accomplished by sending ROS commands via a RFD 900X radio on the 900 MHz band, utilizing 2 high-powered transceivers. On board the rover and at the base station, there are 2 omnidirectional antennas for data transmission. The transceivers utilize amplifiers to ensure the strongest signal for long-range communication. This data link maintains a maximum latency between 0.2 and 0.5 seconds. Video signal is sent from the rover over the 5.8 GHz band using a high-powered transmitter and an omnidirectional antenna.
The rover uses the Robotics Operating System, or ROS, for teleoperation, including control of the wheel motors and LED indicators. The base station ROS node takes input from a Logitech F310 gamepad, translates it into compressed packets, and transmits these to the rover's onboard ROS node, which then uses a Python script to send useful commands via Arduino to the wheel motors. The rover utilizes a ROS-RViz simulation with an A-star search algorithm and input GPS goal coordinates for autonomous navigation. This adaptive simulation implements an occupancy grid with no-go zones for obstacles created from ranging and cloud map data provided by the onboard RealSense camera. Once the rover reaches the provided GPS coordinates, it implements another A-star search pattern from its current position to locate the AR tag indicating the goalpost. Once the AR tag is found, a marker is placed at its location within the RViz simulation. The rover then moves to within 3 meters of the goalpost and changes its LED indicator to flashing green to denote mission success.
To complete the science mission, we will be using a custom-designed Raman spectrometer to search for signs of life. We have selected this method because it is rapid, non-destructive, and applicable to searching for biomarkers in both soil and stone specimens. A Venturi vacuum tube will be used to collect a soil sample that will then be dissolved in acetone and separated with a centrifuge. The Raman spectrometer uses a laser to illuminate the analyte samples. Collected spectra will be compared to a spectra database to determine the presence of biomarkers.
The main biomarkers we will be searching for are carotenoids. Carotenoids are organic pigments produced by plants and microorganisms that serve as protectants against UV radiation. These can only be produced biologically, so any presence of them in our samples will indicate the presence of extant or extinct life.